Okay, so the first thing that I wanted to bring to you guys' attention is case studies. So for the case studies, you'll notice I've updated these folders. There's 2 new things in the folders. There is a PowerPoint that normally I would use to go over the case studies, but because of me being sick this semester and other reasons, like doing the activity, other things that I've done this semester, we're pretty much going to be out of time. But what I want you guys to do is read over fungi, and I think the second one on the list is meningitis, for next class. And any questions that you guys have, I'll answer, but I'm also going to update this PowerPoint that's here to have more of the answers in it than it did before, okay? Because usually what I would do is have you guys write them in during that lecture, and that's why they're not actually in the PowerPoint. So I'm going to update these PowerPoints, but this is a good starting point for you guys, right? And so then the other thing is I've added some pages from another textbook that I use, and I find it does a little bit better job in the way it outlines diseases and stuff like that. So it's an extra good, and there's most of them aren't too many pages, although the fungi one has quite a bit of information, but it's, you know, it's good information. These files, this XPS file is from the ebook that I copied the pages from. So I don't know if you guys are going to be able to open that. So I scanned it. If you can, open this one because it'll be in color. But then I scanned in black and white so you see the PDF. So one of these 2 files should hopefully open for you to be able to read through information on fungi. And then most of the case study too I have embedded into the PowerPoint. It just doesn't have the pictures and stuff. So here's the case study, and again, most of the questions that I have here I have embedded in that PowerPoint. Except I don't remember what edition of updating. So like I said, eventually I'll get it all updated. So my goal is that I will have fungi, and let's see who's the next on the list. Meningitis. We'll work on, I'll have those 2 ready, and I'll field any questions that you guys have. And in fact, I'll maybe even ask you questions and make sure you've read these before class on next week. Okay? And then the following Thursday, we'll do shigellosis and hepatitis, and then Giardia, and then I actually have one more, but you guys aren't going to have to do it, and I'll explain that one on Thursday. So we're going to have a total of 6 of them that we'll go over 2 each day before our test. So that's it for that. The next thing I want to go over is that you guys had the benefit, since you're my afternoon class, that I actually typed up a list for antibody actions, because my morning class didn't understand what I wanted them to talk about. So you guys had the benefit of this slide, and I also printed it out for you guys today. And I made one small addition to it, in that I put cross-linking can form immune complexes. And this is related to the second page of the handout that I gave you guys today, which is related to our next topic, which is disorders. And the main reason I gave you that page is it talks about a condition called serum sickness that your textbook doesn't talk about at all. And it's one of the things that I want to talk about. So I wanted to make sure that you guys had that reference information at your fingertips. I also scanned that page as well and I'll put it in Blackboard. So anyone who's absent today has access to it as well. So let's review. So for opsonization, that action of antibodies, how would you describe what is happening when an antibody binds, and it's this process that we call opsonization? So one person raise their hand if they want to. You forgot about opsonization. Anyone can explain opsonization? All right. He's going to go ahead and try and explain it. Give him a chance to do so.
Eating the cell, tagging for destruction.
Tagging for destruction. So the antibody binding, and the cell is going to, whatever it's binding to, it's going to get eaten. What is it going to get eaten by? phagocytes, right, neutrophils, macrophages mainly, right, can recognize something coded in antibodies, right? So that coding of antibodies, it opsonizes it, it basically tags it for destruction. And the reason why those phagocytic cells like macrophages can grab onto it is they have a receptor for that part of the antibody they grab onto. And what part of the antibody do they grab onto? It's that part that sticks out, or the stem, but we have an actual abbreviation that's used. The FC, right? The FC portion of that antibody is very important for the phagocytic cells to be able to grab onto it. Now, cross-linking is antibodies and antigens binding, and this is, remember, antibodies at the very least have 2 antigen binding sites. IgM, which is mega big, right, has 10 antigen binding sites. It can really cross-link a lot of stuff. So you get what's called immune complexes if you have what's called a soluble antigen. And there's a term that we use for cross-linking with soluble antigens as opposed to insoluble antigens. Which one is soluble antigens? Is it precipitation or agglutination? All right, how many people say precipitation? For soluble antigens. Soluble antigens. How many people say agglutination? It's precipitation. It's precipitation. So think about it this way too. If something can be in solution, right, it's soluble. And that's what they're meaning here. Where when you have a whole bunch of antibodies binding to it, it becomes molecularly very big, so much so that it falls out of solution. That's precipitation.
Right. Forms a solid.
Right. Form something more.
Is for precipitation, and insoluble
Is agglutination, yes. Insoluble things, very large things like bacteria, red blood cells, right? That reaction is referred to as agglutination. And you can sometimes even see that, especially with red blood cells, with the naked eye. You don't even need the aid of a microscope. You can see that clumping effect, that agglutination that happens when antibodies cross-link with antigens and form these complex structures. But when we refer to immune complexes, right, especially as it relates to serum sickness that we're going to talk about next week, it's a soluble antigen, right? It's a small soluble antigen. Now, next on the list is neutralization, and this is distinct to viruses and toxins. So when the antibody binds, it's said to neutralize a toxin or a virus. Because what is it stopping these things from doing that they need to do to harm us? Attach, right? They have to attach. Viruses have to attach to our cells and then gain entry, right? Toxins have to attach to our cells, and even some of them gain entry into our cells. If they're coated in antibodies, can they attach to us? No, we've basically created a barrier, right? We've surrounded them so that they can't attach to us, right? So that's one particular way in which antibodies act and help us. Now, immobilization stops stuff from moving. So bacteria, what do they have appendage-wise that helps them move? Flagella, right? And so the antibodies can bind to the flagella and wrap them up and tangle them up, and they get stuck and they can't move. Preventing of adherence. So same thing with bacteria. In order to cause infection, most of them have to stick to us. So if our antibodies stick to them before they stick to us, it really helps prevent infection, okay? And there's one class of antibody that we actually secrete into our mucus and our secretions that's really good at this particular action of immobilizing and preventing adherence, and that is IgA. Good, good. You're good. We're just reviewing from the activity. So, yeah, I know. And I want to thank the people who did recordings for me, because I don't know if you guys seen it. I posted them, the video recordings I did of me drawing on the board during our activity. They all came out really good. So it ended up being in 4 parts because, remember, the batteries died. So they came out really good. So those are a good resource there for you guys as well. So the next one is complement activation. So do you guys remember which pathway? There's 3 different pathways for complement activation. Which one is started by antibodies interacting with complement? Classical pathway. Correct. It's the classical pathway. But all pathways, doesn't matter how it gets started, right, have these possible outcomes. You can have the production of C3b. And what does C3b do? What does it do? Opsonization. It tags for destruction, right? C3b, remember B for binding? It's going to bind to the surface of the bacteria, right? And our phagocytic cells, in addition to the FC receptor for antibodies, they have a C3b receptor, macrophages do, so they can grab onto these cells and engulf them and kill them. Right, so we're tagging them, we're opsonizing them, we're tagging them for destruction with C3b. C5a and C3a both are involved in a very important immunological response. Inflammation, right? So we've got complement activated by the antibodies. So the antibodies are going to help opsonize and get us to destroy. Then we're going to throw some more C3b on there. And then with the C5a and the C3a, we're going to call even more macrophages and neutrophils to the area to gobble these guys up and destroy them. And then we could even go even further in destruction, right, and the formation of the MAC complex, which is several of the complement proteins that insert into what? What does MAC stand for? Membrane attack complex, right? So they're going to form that donut-shaped complex, right, and lyse those cells. Now, as far as bacteria go, gram-positives and gram-negatives, one of them is more susceptible because their outermost covering is a membrane. Who is that? Gram-positive or gram-negative? Gram-negative. Gram-negative have that outer membrane. So they're more susceptible to lysis by the MAC complex. And then the next action is a very specific action. Oops, one thing I didn't mention here. Complement activation can only happen with 2 classes of antibodies. Which 2 are they?
IgM and IgG.
Yep, IgM and IgG are 2 main ones. Antibody-dependent cellular cytotoxicity is a unique situation where only one class of antibody can cause this to happen, and that is IgG, right? IgG. And the reason being is, again, that portion of IgG that sticks out, the FC portion, is unique to the IgG class antibodies. So only this lymphocyte can grab on to that IgG when it's attached to a cell. Now this can be one of our cells or a foreign cell, right? The antibody is coating a cell, right? So notice again, antibody dependent cellular, as in we're going to kill a cell, right? This is attacking a cell. Cytotoxicity, of course, referring to the fact we're going to kill it. Who is actually going to kill it? Which lymphocyte is going to bind to the FC portion of IgGs attached to cells? Natural killer cells. Natural killer cells. Now, natural killer cells are lymphocytes, but they're quite different from B cells and T cells in that B cells and T cells have receptors specific for antigen, right? B cells have their antibody, which is their B cell receptor, and T cells have their T cell receptor. And remember, that's specifically recognizing a specific antigen, those receptors. Natural killer cells, no antigen-specific receptors. The only reason they're knowing to kill this cell is because it's coated with antibody. The antibody is what is specific for the antigen. Right? That's what's determining, and that's why it's dependent on the antibody, right? That's why it's called antibody-dependent cellular. We're coating a cell in antibodies. Cytotoxic, we're going to kill it, right? Because that antibody is basically tagging it for destruction, but instead of like opsonization, destruction by phagocytic cells, instead, we're going to kill it using a natural killer cell. Because we're actually going to kill that cell, that human cell. So we looked at these cute little guys, right? Cute little dendritic cells. And this is just one of their abilities, is that they can take in antigens, and the very important next step is to present it, right? What we call antigen presentation. And this does this by a particular marker, right, that it has on its surface, that it picks up the antigen and it presents it. Now this guy has both class 1 and class 2 MHCs, right? That's the marker that it's using to pick up the antigen and present it. And in this case, it's presenting it to a helper T cell. So which MHC is it using? Class 1 or class 2? Class 2, right? Because helper T cells can only communicate with MHC class 2. That's it. And part of the reason for this is with the co-receptor they have. They have CD4. They have CD4. And that allows them to communicate with this dendritic cell. And then as their name implies, they help, right? Once they become activated, they're going to proliferate. Remember, we're going to end up with a whole bunch. And remember, this T cell receptor right here is specific for that antigen that the dendritic cell is presenting. Okay? So he's got his number. He knows this bad guy. So he's going to proliferate, right? And some of them are going to do just as the name implies. They're going to go out and help other cells, right? And then also, what are we going to produce that are going to stay in our lymphoid tissues and our lymphoid organs in case we see them again? Memory cells, right? So we're going to memory CD4 helper T cells. Who can this guy go help? What other white blood cells does he go help? B cells and macrophages, right? Macrophages, they're going to help them increase their killing ability, right? Become really super killers, increase in size, just go nuts, right? B cells, what is the main job of a B cell? What?
Antibody?
Yeah, we want to produce antibodies, right? Actually secrete antibodies. So sometimes in that process, right, when you have this naive little B cell, right, hasn't seen its antigen yet, but oops, now he has, right? It's bound to his antibody on the surface, and we drew this better to look more like an antibody with 2 antigen binding sites that day, right? We improved upon this drawing. But he's like, oh, this one fits, I know this guy, right? So then can he produce antibodies?
No, if he has the receptor.
If it's what we call a T-independent antigen, right? He could go right to producing plasma cells and secreting antibodies. But sometimes it's what we call a T-dependent antigen. So who needs to talk to him? Who's going to help the B cell? The helper T cell. So that's the interaction they're showing here, right? Here's the cute little B cell with his bound antigen. But what they're not showing you is that he internalizes this and presents it, right, to the helper T cell. He presents it on MHC class 2, right? And he's going to communicate with the T cell receptor, right? If the T cell receptor recognizes it, and plus he's got his co-receptor, CD4, that allows him to communicate with this B cell. Now, this T helper cell was probably previously activated by a dendritic cell, right? Now he's going to help the B cell become activated, right? So when we think activation, we think proliferation, right? Lots of these B cells, okay? Some of them are going to be long-lived memory cells. Others are going to turn and differentiate into plasma cells. And what do plasma cells do? They secrete antibodies. Eventually they will die, unfortunately, when their job is done, but not yet, right? They're going to secrete antibodies. So we have a cute little drawing here, right, of him like spitting them out. He's going to increase his rough endoplasmic reticulum, right, because that's going to produce secretory proteins that are secreted, which is what antibodies are, right? And then here it's binding to the bacteria, right? The antibodies by themselves, and then along comes Mr. Macrophage, right? And what is he going to do to this bacteria? He's going to gobble them up and eat them. Why? Because they're coated in antibodies. And what type of action do we call this in antibody actions? What has this antibody done? It's tagged them for destruction, but what's the proper term? They've been opsonized, right? They've been tagged for destruction. And that's pretty much the end of the story, right? This is going to continue on and on. Antibodies are going to keep producing antibodies, right, until we get these guys all destroyed and eliminated from the body. If we see them again, our response is going to be much faster because the antigen's probably going to come in contact with who? A memory B cell, right? But same process is going to happen again, right? This guy may need to be activated by a helper T cell or might be able to move right to plasma cell, memory cell, more memory cell production, producing antibodies, opsonization, destruction, right? Get rid of them. So this process that we go through for producing antibodies, when we start talking about disorders next, it's the same process, right? The only difference is that, you know, unfortunately our immunological response isn't necessarily what we want in that area of our body or under those particular conditions. But whenever we talk about antibody production, we're talking about a B cell getting activated, turning into a plasma cell and secreting antibodies. In that process, right, we may have helper T cells involved, and we're always going to get memory cells produced of those helper T cells, those B cells. Who am I forgetting? Is antibodies like the only thing we do? No. That's our humoral response, right? Antibody production. Especially with viruses. Do we want just antibodies? No, because that's only going to neutralize them when they're outside of our cell. Antibodies cannot get inside of our cells. So who do we need to help us out in eliminating those things that get inside of our cells? Who's going to help us with that? Natural killer cells can help. But what other lymphocyte that could be activated by a dendritic cell? The cytotoxic, right? The CD8, right? And the difference there, right, is which MHC is the dendritic cell using that time? Class 1, right? So dendritic cells have the ability, and macrophages have the ability to do both, right? Our somatic or nucleated cells can also present using MHC class 1. Who's going to come along and kill them? Right here in the cute little drawing, they have killer T cell. But in truth, this would be a cytotoxic T cell, a CD8 T cell, right? So when viruses get in, when bacteria get in, when cells behave badly under cancer conditions, these cytotoxic T cells can recognize this. What's so funny? Oh, the gun. I know. Right? It really shows killing, though, right? Guns really do kill. Unfortunately, a little too often lately. Don't even get me started on that. But, yeah, that's his job. And in this case, we need him to do that. This is one of the things I printed out for you guys. Anyone who came in late, there's some handouts by the sign-in sheet. That's why the sign-in sheet's there. Hopefully everyone grabbed that. So the first page is this, and then the second page I just reprinted out about the antibodies so that you would have it. This is, again, from another book. And what I like about this one is it's kind of a summary of everything that could possibly happen and may happen when we're exposed to something. So remember up here, the whole story when we're talking about B cells and T cells starts in our primary lymphoid organs. It all begins in our bone marrow where they're born, right? And then the B cells are going to leave. They're mature from the bone marrow, and they're going to go to our secondary lymphoid organs. So what are some examples of secondary lymphoid organs? Tonsils, yep. Adenoids. Filter, what filters lymph? What filters lymph? Lymph nodes. What filters our blood? The spleen, right? And then you have your appendix as well. And then you have tissues, right? You have mucus-associated lymphoid tissue. So it's not organized to the organ level, but it's chock full of these B cells and T cells and macrophages, and dendritic cells are going to travel there as well. So you have the mucus associated and you have the skin associated, right? So we're covering those major barriers, those major entry points that could happen. Okay, so we cover all our bases. We filter the lymph, we filter the blood, right? We're right there at the barriers, at the skin and at the mucus level, right? Even inside the intestines with the appendix. Nose and throat, major entry points, right? You're always constantly breathing and potentially eating. The good news is that you have that protection right there of your tonsils as well as the lovely acid in your stomach, hopefully, right? So hopefully by the time it gets to your intestines, they're not gaining entry. So in these areas, right, is your B cells and your T cells. Remember your T cells, they have one extra stop before they travel to these lymphoid organs and tissues. They've got to go where? Thymus, right? And it's called primary because that's where they learn the difference between self and non-self, right? If they recognize self, they're eliminated. For B cells, that happens in the bone marrow, right? They're not let out unless they're A-OK, right? Remember, we have the two different types of T cells, and they have to go through that selection process in the thymus, right? That's why they're named T cells. So we have our helper T cells, right, that can help, as we've seen, the B cells, and as drawn over here, travel out and help out macrophages. B cells, right, the normal progression, when they become activated either on their own or with helper T cell help, they're going to produce those plasma cells and secrete antibodies. And the B cell memory cells are going to stay behind in the lymphoid organs and tissues for in case we see this bad guy again. Right, and notice even the plasma cells themselves will leave things like the lymph node and stuff like that and travel to the areas where the infection is and produce the antibodies right on site. How do they get exposed to the information? Well, it depends on where they are, right? If they're in the spleen, it's something they filtered out of the blood. If they're in the lymph node, it's something that maybe have traveled through the lymph. Right? Or it might be something a macrophage or a dendritic cell brought to those areas, right? So remember, these guys are our main presenting cells. They're going to bring it and present it to the helper T cells and the cytotoxic T cells. Or antigen all by itself could come along, right? And that's what they're showing you here. Antigen all by itself can come along and interact with that B cell and get that activation process going. Cytotoxic T cells, right, these really cool killer CD8 cells, again, would be activated by a presenting cell coming along. T cells have to have antigen presenting to them. So a dendritic cell or a macrophage in the particular area they're in is going to present to them. You're going to get, again, notice memory cytotoxic T cells that stick around at the activation site. But you know, this may be because virus-infected cells somewhere else, right? So these guys also notice they're leaving the area of the lymph organ or tissue, and they're going to go out to the areas where they're going to do their job, and in this case, killing defective cells, infected with bacteria, virus, cancerous, whatever it is that's triggering them to destroy them. So I talked last time a little bit about leprosy, right, and about how some individuals will go, your immune system is unique to you, right? So your immune system, for some people, unfortunately, that get leprosy, they go all the way to the humoral send, the antibody wing, right, what is called the prominous leprosy. And this is bad news because this is an intracellular bacteria. So once it gets inside of our cells, do antibodies do us any good? No. Right? It can't get at them inside of our cells, okay? Unless, you know, somehow our cell is presenting pieces of it, and they just don't do that on the outside. And so antibodies are only going to do you a little bit of help. Then there's some people that go completely to the other side of the spectrum where they do just a cellular response. And that's great, right? Because then they're going to kill the cells. The bad news is with leprosy is that this will invade the peripheral nerves. It likes cool regions of the body. And so this is why you would see the deformities, right, in people's hands, feet, face, their nose, their ears, because that's where there was large collections of the bacteria and our immune system was killing them. Well, unfortunately, it kills the peripheral nerves in the process as well, right? And so then they would end up with deformities. And they may they would live longer than people who were completely on the lepromatous scale, because completely on the lepromatous scale, it will invade internal organs and it would shut down, and the person would die. And then there's variations in between, where there are some people that do a little bit of both, and that would probably be the best case scenario, where you have both antibody and T cell production. And the same holds true with like viruses, right? We don't just want a T cell response, a cytotoxic T cell. Antibodies can be beneficial too in the neutralization ability that they have. But some people, for certain, and leprosy is a really interesting one, because they really have the dynamic that can happen. And, they say, diseases run in families and stuff like that. Well, that is twofold. If you're a family, you probably live together, right? You're exposed to the same type of environment. So especially if you're talking about a contagious disease, which leprosy is, there's still about 100 new cases each year in the United States. And a serious problem actually in India, leprosy, yeah. And here in Louisiana was the last leper colony in the United States, outside of Baton Rouge and Carville, Louisiana, St. Gabriel Parish, right off the river. A couple of nuns from New Orleans snuck a whole bunch of leprosy patients up the river many, many years ago and began that place. And it became a center for the research. They have an excellent museum there. There are a few patients, and people came from all over the world. I think there's a gentleman there, he's from the Philippines originally. They came from all over the world to get treatment and help. And for some of them, they've been there since, forever ago, and so they've known no other place. So they still have homes there on Carville, and some come and help at the museum. So that one gentleman, I can't remember his name today, for the life of me. One of his hands, he doesn't have any fingers because of the debilitation of the disease. Now we have antibiotic treatment, right? It's treated on an outpatient basis. If recognized early, hopefully don't have as much damage and therefore won't potentially lead to the deformities. One patient was telling a story about one time he was in another patient's room and he put his hand on a hot plate. He didn't know it was on. He couldn't feel it. He did not know he was burning his hand until he smelt it. So like diabetics that deal with peripheral nerve problems, they are always constantly having to check and make sure they don't have any minor wounds that could potentially get infected, because they could get cut and they don't feel it at all. They don't even know they've been injured. So that's a really cool place to check out. I used to have a really cool video and I let someone borrow it. She swears she gave it back, but I can't find it. But anyways, very interesting history on many different levels as far as leprosy goes. But from an immunological standpoint, very interesting disease as well. And really helps drive home. So in addition to, people, families having the particular disease, well, exposure would be very similar if you're a family. Plus, genetically, you're very similar. So think about it. Your genetics determine which way your immune system's going to go. So in the case for these individuals, their immune system would go a particular way, so you'd have the same infection within a family, right? And the other thing that's nice about this is that there's actually a small percentage, they believe, of the population that's actually even susceptible to this infection. Most of us, our immune system is actually be able to eliminate, the macrophages are able to destroy it and not let it grow. Where other people, they have this defect, right, and they're not able to kill the bacteria. Their innate immune response isn't able to eliminate it. So then they've got to go to adaptive. And adaptive, depending on which way they go, right, can also not necessarily eliminate the infection for them. So really fascinating immunological disease for sure. So that's, the main basis. Those are the main important points, right, for our adaptive immune response. There's some little more details that we didn't get to last time that I want to make sure I address this time. So we've talked about, right, this humoral response, this antibody response. And this is one of the most common responses to infection, but also not the only, right? We have that cellular response that can happen with cytotoxic T cells as far as our adaptive immune response goes. T cells, Antibodies we can very easily measure, right? They're secreted into your secretions, also into your blood, right? We can take a blood sample and get an idea of the number of antibodies you have. This can be calculated to a number, and this is typically what we refer to as a titer. So in my other microbiology class, I've got a bunch of students that are getting ready to go to nursing school, right? So they're all talking about their titers and their vaccinations, because you have to have everything, all your vaccines up to date. And one of the ways they can, if you don't know your vaccination status, is they could take a blood sample and determine your titer, your level of antibodies that you're still producing for that particular vaccination, or if you had the infection. So like for me, for chicken pox, I knew if they took my titer, I'd probably be positive because I know I had chicken pox, right? Where my son would have been vaccinated and hopefully he would have a titer from that, right? So there's no way of knowing if you have a titer, if you had the infection or if you were vaccinated. The good news is you've made an immunological response that we can measure, which is antibody production. So the bad news, though, is that sometimes it takes time for those steps to happen that we looked at, to find a naive B cell that recognizes those antigens, right? And maybe wait for the T cell to help out that B cell before it goes to actually putting the plasma cells and secreting antigen. So we refer to this period when antigen is present before antibodies are detectable as the lag period, right? And this can be quite substantial, 7 to 14 days, right? My slide says 10 to 12, but yeah, 7 to 14 is the more widely accepted numbers, right? So think about this too. How did you get exposed to that antigen? You could have been naturally exposed, natural infection, like I was with chickenpox, or in the case of my son, vaccination, right? Vaccination might be your first exposure to antigen. It's going to take time, if your body does it, and hopefully it does, to produce antibodies against what you've been vaccinated against or what you've been exposed to. Now, in the case of a natural infection, your innate immune response has to keep you alive, right? Until adaptive kicks in. If you even need adaptive to kick in, maybe innate will take care of it all on its own, right? Maybe your macrophages and dendritic cells are going to clean it up all on their own. But a lot of times we're going to go to additional adaptive response. So as you can see in the graph, we most commonly produce IgM first, and then a lot of times we'll switch to producing IgG. And we're going to talk about that in a moment, about what we call class switching and why we have all these different classes. Are you looking for someone in here?
Oh, they say 107 needed to be open.
Maybe wrong building.
No, this 107 East is the like.
Oh, I've been in here. I'm good. Miscommunication. I don't know, some idiot locked our copy room the other day. I come in the morning to print out my quizzes, I'm like, who locked this door? I don't know. It's all good. So this first exposure, the scary thing is that time, that lag. And the good thing with vaccination is that you take care of that in a safe way, that hopefully you get past, not hopefully, you get past that lag period and you've already produced all these memory cells. So that the second time you're exposed, naturally, potentially, to say measles, right, then you already get those memory cells. So your lag time could be minimal, right? Minutes, days, hours, who knows, right? But we're not talking 7 to 14 days anymore, okay? And the response is going to be that much greater because your body's seen it before. It knows it's a bad guy, right? It's got its number and he knows what it's about. And so you'll see IgM will be produced, but if there's a switch that needs to be made, it's made very early, right? And it just skyrockets. And they're going to continue to produce it as long as the antigen is present. When the antigen is no longer present, the antibody production is going to decline quite steadily because we don't need them anymore, right? Why are you going to produce something that you don't need? So the same holds true for those plasma cells. They're going to undergo apoptosis after a few days when antigen is no longer present. Apoptosis, remember, does not elicit inflammation, right? This is programmed cell death. If every time one of our cells died, we went into inflammation, we'd be in a constant state of inflammation. Okay, why don't we keep around these plasma cells, right? With these huge, rough endoplasmic reticulums that have the ability to just spit out antibodies.
Too much, you can't have too many.
Yeah, I mean, that's a cell that we don't necessarily need because we have another cell that'll take care of it if we see this again. And what is that one? Memory cells, right? Those are what we maintain, right? The plasma cells are like the workhorses, right? Once their job is done, okay, you're done. We're not going to maintain you anymore, right? You're too expensive. So titer, as I said, right, refers to the concentration, literally a number they can figure out, of antibodies that you have present at any one time. So these are just some pictures of what B cells can look like, right? This is a scanning electron micrograph. You can see all its receptors and stuff on its surface. This is a slice of one that's a plasma cell, so you can see that really big, rough endoplasmic reticulum. And this is what they would just look like under the light microscope, right? The nice big nucleus, little tiny cytoplasm. Of course, it would get much larger when they're a plasma cell, but really would you see one of those in circulation? So we talk about this process of selection, right? Clonal selection. Once that B cell is selected, once it's become activated, it proliferates. And clones implies that it's an exact copy. Not really. Almost exact copy. They go through a process referred to as affinity maturation. And as they divide, they're going to do purposeful little base substitutions to their variable region of their antibodies. And the reason for that and the hope is that they will bind their antigen stronger, right? That they will have a change and it will adhere to that antigen much stronger. So notice this one they coded as a ++, right? That's a pretty good binding, right, to the antigen. Well, these cells copy, right, multiply, proliferate. This particular prodigy from this one has a little bit less binding ability, only scored about a 1+. Because of that, it's not going to be signaled to continue to proliferate because 1's not good enough, right? So we're going to keep signaling the 2+. But if we come along and we get a 3+, right, where we've mutated, right, and changed that variable region so that it's really grabbing on, right, to a 3+ level, grabbing onto that antigen, then that lineage is going to be stimulated to continue to proliferate and the 2+ are going to get shut down, right? We want the best possible fit for that antigen, right? So in the process, as the B cells are proliferating, they're going through this additional selection process, this affinity maturation. They want to get better and better. So helper T cells can induce some B cells to become plasma cells that secrete their antibody classes. So in addition, there's communication that happens in the different areas of our body. The first antibody that a B cell will typically produce is IgM, right? And what determines the class of the antibody, remember that characteristic Y structure? We've got the variable regions of the light and heavy chains, and then there's that heavy chain portion of the two heavy chains that sticks down. Some people refer to the stem, or we know it as the FC portion. That portion is different for each class of antibody, right? So in our DNA is encoded all the classes, right? And so IgM, you'll notice, is first, right? That's the first one we're going to make. But some cells are going to go through genetic change. They're going to go through the process of class switching. Well, they'll cut out the M and the D, say, and switch to producing IgG. This is a very common switch that happens in your lymph nodes, right? Your lymph nodes, for the most part, are going to produce IgG. Your mucus-associated lymphoid tissue, on the other hand, IgG is not going to do you any good, right? You want IgA, right? Because that's the one we secrete. That's the one that's going to immobilize and stop adherence. And then there's a class that we haven't talked too much about yet, and that's IgE, because Erica absolutely hates that one. Because that one is related to what we're going to talk about next in disorders, what was referred to as allergy. So some of us, under certain circumstances, are programmed to make E. And what's bad about E is how the immune system responds to that specific class of antibody. Right? And so in my other class, some students had mentioned, and were thinking ahead about IgG. IgG can cross the placenta. This is the one that moms, if they're Rh negative, they don't have that antigen on their red blood cells. If they're exposed, right, if we get that activation of B cells that know how to make antibodies against Rh, they're going to go IgG route. Why? I don't know. That particular antigen, we just go that route. The bad news with that one is it crosses the placenta and can attack the baby's red blood cells, and you get the condition referred to as hemolytic disease of the newborn, right? ABO blood group, right? Those are antigens on the surface of our red blood cells as well. We don't run into problems with that though, do we? The reason being is we just produce IgM against those, right? So you really only run into problems when you have blood transfusions of the wrong type. Your baby you don't have to worry about because IgM is too big. It doesn't cross the placenta, right? So it's not going to create those problems. Right? So the class of the antibodies, right, our immune system responds differently to. We've already seen how IgG is the only one that can cause antibody-dependent cellular cytotoxicity with natural killer cells, because that's the only class that he's got a receptor for and he can grab onto, right? So our body responds to the different classes in different ways, and the antibodies themselves have different abilities. Where IgG, as I said, can cross the placenta, right? It's the only one that does that.
So you said like only some people make IgE?
Everybody makes IgE, but against what and to what extent varies from person to person. Your immunological response is programmed in your genetics. Right? So the unfortunate thing for people like myself is that allergies are inherited. So I inherited them from my mom, who God only, I don't know which grandparent I have to blame for that. And then my son has me to blame for his allergies. He inherited them from me. So the predisposition to having allergy he inherited from me. Actually having allergy was due to exposure and actually going that route of IgE, which is one of the things we're going to talk about next time. You have to have that first initial, what we call sensitization, where the same thing as what we've been talking about antibodies, it's your initial exposure, right, to where you produce the antibodies. But also, in addition to antibodies, what did you produce? Memory cells. So each time you're exposed to that antigen, or in the case of allergens, each time you're exposed to that allergen, you produce more IgEs, and more, and more.
So why do people that eat a lot of, they're allergic to peanut butter, they say they take it over a long time, and they can just eat it normally? Why does that happen? I'm confused what the question is. So they eat peanut butter, and then they become allergic? Peanut butter, so they take little bits over
Oh,
a long
okay,
period of time.
yeah.
What is that about?
Okay, so that is referred to as trying to desensitize. So I'm going to actually leave that one for later because we are going to talk about it. We are going to talk about it. I don't want to get into it now. I don't want to confuse anybody. Okay, so what am I forgetting? We went over, don't forget about good old natural killers. We have just these two last things left, and then we'll be done. So we've already talked about one of the abilities of natural killer cells, right? And that is this antibody-dependent cellular toxicity. So a cell coated in antibodies that the natural killer cell can recognize. Remember, this is only IgG antibodies that it can recognize and will kill. Another one is right here, where you have a cell, say, infected with a virus. All the time, your cells, your somatic cells, your nucleated cells are picking up antigens, self-antigens, right, and presenting it on their surface in MHC class 1. But if they're self-antigens, right, cytotoxic T cells aren't going to recognize and kill this cell. But this is a process that they continually always do. They're always presenting their insides basically on their outsides for inspection, right? They're always being inspected. Make sure they're not doing anything they're not supposed to. Well, one of the things that some viruses will do is shut down this mechanism of MHC presentation on the surface, MHC class 1. So all of a sudden you have this cell that doesn't have any MHC class 1 on the surface. So cytotoxic T cells can't communicate with it, right? Because it's not presenting. So instead, our backup here is our natural killer cells. Natural killer cells come along, right? And they're surveying the cell and they're like, you're not doing any antigen presentation. There's no MHC1 here. What are you doing? This is not what you're supposed to be doing. So what's the natural killer cell do? Kill it, right? Because it's not doing what it's supposed to do, right? It's not presenting MHC class 1. There must be something wrong with this cell. The natural killer cell will kill it, right? So they are constantly surveying and looking out for our cells for when they're doing stuff they're not supposed to do, or in the case of antibody dependent, when they've been tagged for destruction, right? Because there's clearly something antigenically wrong with them, right? They're displaying some type of antigen that our antibodies have detected as being bad. So as I said, and this is just in words, right? What we've been going over. And then that was from our activity. So handout I gave you today, I'm going to post on Blackboard. Please read that second page of the handout. It deals with one of the hypersensitivities, the disorders that we're going to talk about next. Definitely by Friday, I will have the new PowerPoint posted for you guys for disorders, which is our last topic of immunology. And remember, our exam for this class is, yeah,